What's up, people? This should be a real quick one. Should be. We have to get into this idea of fields, right? I've tried to do my best to mention it a little bit here and there in the last, certainly when we do gravitation, we mentioned it, and that's why we start with this mention about gravitation here. And we actually mentioned it when we talked about, I think, one of our electrostatics problems, right? And the deal is this, that if we go back a few weeks and we say no matter where you put a mass near mass m, it'll experience a gravitational force. The question is, why is that? Well, if I put a mass, here, we'll call it little m, well, it feels a force like that. If I put a mass m here, well, it'll feel a bigger force. That doesn't necessarily have to end right on the circle, right on the mass m there, so we'll make it not. It could feel a force like this, Fg here, Fg here. And even a different size mass, well, a bigger mass right here would feel, a force like that, Fg. Well, why all these forces? Why do these forces exist? We say because at any location, really every location, mass m, that one, creates a gravitational field that we call G in the space around it. And it's that field that exerts a force on any other mass, like this one, or this one, or this one, that you place in the field. Okay? Now the analogy to electrostatics, right, is that, well, instead of placing a mass somewhere in space, we place a charge, I'll call it capital Q here. We'll talk about why that's a capital Q soon. So the deal is no matter where I place another, here's a Q, an additional charge. Well, let's see. This one could feel a force. Well, let's call this a positive, and we'll call this a positive also. Well, this one would feel a force, I don't know, like that, right? Fe. We put a charge, well, how about in here we make it positive? Well, that's going to feel a much bigger force, Fe, like that. And, well, what if here's a curveball, what if I put a negative charge here? Well, that's going to feel a force this way, Fe. But no matter where we put another charge, it'll experience an electrostatic force. Right? Like on the last page, real important, no matter where we place an additional mass, it'll feel a gravitational force. Well, charges placed near other charges feel electrostatic forces, not gravitational forces. I mean, they could feel gravitational forces based on their mass, but based on their charge, they feel or they experience electrostatic forces. Now, just like masses create gravitational fields, charges create electric fields. So why? Well, it's similar to the last page, right? We said here, at every location, mass m creates a gravitational field in the space around it. Well, here, we say, at every location, charge Q creates an electric field that we call capital E in the space around it. That might be redundant, at every location and in the space around it.
John Brady, please.
I could just say charge Q creates an electric field in the space around it. And I will say this, that field is responsible for the force on any charge Q placed in the field. All right, now, when we look at gravitational fields, you'll notice that no matter where we put a charge, sorry, a mass, this can be confusing. No matter where we put one of these masses, it's always attracted to mass capital M. All right, and that means that gravitational fields always point toward mass. So if I said, here's the Earth, the gravitational field near Earth can be represented by a bunch of vectors that point inward. We would call those vectors gravitational field strength vectors, or gravitational field vectors, okay? The deal is with charge, however, there's two kinds of charge, right? There's positive charges that would be repelled from this positive charge. There's negative charges that are attracted to it, so we just come up with a sign convention, or with a convention, and the convention is this, real important. Electric fields, by definition, point in the direction of a force that a positive charge placed in that field would experience. You absolutely have to memorize that. It's not too much to do, but it's super duper important. Electric fields point in the direction of a force that a positive charge would experience if it were placed there. All right? So, electric field lines always look like this. Well, anywhere around this positive charge over here, this positive charge, anywhere around this, no matter where I place a positive charge, whether it's there, or there, or there, or there, or there, or anywhere, the force that it feels will always be what we call radially away from this charge. So electric field lines always point away from positive charges. Come here, dummy. Come here. Whoa! Electric field lines always point away from positive charge. Right? Because, again, the field points in the direction of the force that a charge would feel if I were to put it there. If I were to put a positive charge right here, it would feel a force that way, away from the charge. All right? Therefore, the field at that location is away from the charge. Same thing goes for negatives. If I put a positive charge here, because that's the definition of what direction electric fields point, they point in the direction of the force that this charge is going to experience, well, it would be pulled this way, toward it. And that means that no matter where we put that positive charge, near this negative one, the electric field always points toward negative charge. All right, so that's two things. Electric fields always point away from positives and toward negatives. All right, that's all I'm going to tell you for now. The rest of your assignment tonight is that electric field applet activity. All right, the reason we do this first is we just have to be able to know this part, what direction electric field lines point. Because when you draw electric fields, which you're going to do a bunch of tonight, you have to draw the direction of those fields. You have to put arrowheads on your electric field lines. Okay? Now we know what direction to put those arrows in. Sound good? Okay, people. That's annoying. Erase. Come on. There you go. All right, see you tomorrow.